Good afternoon, everyone. Welcome back to our seminar where we're going through mean curvature flow with surgery. At this point, you might think that there's cause for celebration because we've done a lot of good mean curvature flow. However, it turns out that most of the interesting results that we've done only really apply for three-dimensional mean curvature flows in R4 or higher. Turns out we have to go back and treat some of the estimates for embedded surfaces in R3 again. Vishnu has kindly volunteered to take us through this. So Vishnu will be talking about the cylindrical and gradient estimates for mean curvature flows in R3. Thank you, Vishnu.
Thanks. All right. So what I will do is I'll prove these two estimates over the next 2 weeks or so, and I'll maybe point out kind of why it's necessary to do something different for surfaces in R3. So maybe let's start by recalling these two estimates that we proved earlier in higher dimensions. So we had the cylindrical estimate for n greater than or equal to 3, which was, so for any epsilon greater than 0, you can find some constant c epsilon, which depends on the initial data. Oh, well, I should probably say that, this is for if you have a solution to two convex mean curvature flow in n plus 1 for n greater than or equal to 3 is two convex. Then there is, for all epsilon greater than 0, you can find some constant such that whenever the smallest principal curvature is less than or equal to epsilon times h, the difference between any other two principal curvatures is less than or equal to epsilon h squared plus c epsilon. Okay, so what this means is that if I take some kind of sequence of rescalings about a point where h goes to infinity, then in the limit, we'll have that all the principal curvatures, except for the smallest one, will all be equal. Okay, so this is why it's called a cylindrical estimate, is that you have one principal curvature, which is kind of going towards 0 in a blow-up, and then the remaining ones are all going to be equal. And so you kind of expect that if you also combine it with a gradient estimate, that such a limit will be a shrinking cylinder, which is like Sn minus 1 cross R. Okay. So yeah, so then we also proved the gradient estimate. Yep, so that said that. So this was proved kind of using the cylindrical estimate, so that there exists some kind of constant that depends on n, and some other constant which depends on n and then the initial data, such that the gradient of the second fundamental form squared is less than or equal to Cn a to the 4 plus c. Okay, on m times some interval. I think if I do this correctly with like a c, and using this pinching condition, that I know what this thing here is, but I don't know what it is if I don't write it down properly. So m cross some interval. So the reason we proved this gradient estimate was because then what we could do is we could prove these neck detection lemmas, right? So it actually tells you that you do get a cylinder exactly when you blow up. Okay, so when we did these proofs, when I proved the gradient estimate, it was very important that I chose n greater than or equal to 3, because you had this particular estimate, which was something like grad h squared, or is this the right way around? Is less than or equal to 3 on n minus 2 grad a squared, or is it the other way around? Can't remember, but we use this kind of thing over and over again in order to prove this gradient estimate. Now, just looking at these estimates, firstly, the cylindrical estimate, it really makes no sense if you set n equals 2 because there is only one principal curvature other than the smallest one, right? So you can't really write it like this, but you can then ask, if I take some kind of sequence where h is going to infinity, then if I'm blowing up about some sequence of points, then do I get something that kind of looks like a cylinder at that point? Like, is the principal curvature just the same as the principal curvature for a cylinder? Okay, so that's what we should be asking in dimension 2, n equals 2. And for the gradient estimate, well, can we prove something like this? Is that possible? That's what we have to do in dimension 2. So, well, if I don't make any kind of other assumptions, the answer to both of those questions is no. So okay, so remember that in the case for hypersurfaces n greater than or equal to 3, there is no assumption on whether or not our compact initial surfaces are embedded or not, right? So all this surgery that we've done, it applies for arbitrary two convex initial surfaces that are not necessarily embedded. They could be immersed, right? But if we take immersed surfaces in for n equals 2, so 2 convex and n equals 2 is now mean convex, right? So I can draw a mean convex initial surface that is immersed, for which the singularities are not cylinders, and also this particular gradient estimate fails. So I'll draw that. So if I just make this kind of loop here, or something, let me make it a bit more symmetric. Something like this. Oh no, okay, I'll do it like this. There we go. That's kind of what I do now. And now I rotate it around this axis here. So I get this kind of loop here going all around the z-axis. And now if I evolve this so this is mean convex, okay? And now if I evolve it under mean curvature flow, then I get something like this. It's kind of cusp rotated around the axis. Now, if you blow up around this point here, then what you get in the limit is, zoom into that, then you get a singularity which is modeled on the translator, the Grimm hyperplane. This cross R. Okay, so I mean, this is clearly not cylindrical. It only has so it's like a hyperplane, so it's not cylindrical. So you can't, so the cylindrical estimate is definitely false. Now, this gradient estimate, on the other hand, well, as it turns out, it's actually also not true. If I look at the quantity nabla a squared divided by h to the 4, well, so this Grimm Reaper, gamma t, that's equal to x comma y comma t minus log sec x. Okay. And then if I calculate this, as it turns out, I get x, y, t, then I get that's equal to something like, oh, actually, I think this has to be cos, actually. And then I get something like tan squared x, something like that. So as I'm going off, as I look at points along this going off to infinity, so you can see the mean curvature is going to 0, and the second fundamental form is going to 0. So, and if I compute this quantity nabla squared on h to the power 4, then as I go to, it's going to be like, it's going to also go to infinity, this quantity here. So this gradient estimate we proved here, the same thing can't be proven. I'm not really sure if there is some other gradient estimate, like if this is like, there's something else you can do, but the solution in the situation for n equals 2 is just to assume that our surfaces are not immersed and just work with embedded surfaces. Right? That works because Yeah, well, so you know that if you start off with a embedded solution to mean curvature flow initially, then that's surface will stay embedded um, until it becomes singular. And even better, um, it's been shown that that if you have, so let me write it down a theorem. Right? So if I have mean convex mean curvature flow, okay, let's say I have a solution x from m 0 t to, well, this is true for Rn plus 1, is a mean convex solution, then the Grim Reaper doesn't, then the Grim Reaper doesn't occur as a blob limit. So is an embedded. Yeah, the Grim Reaper is not a blob limit. So this same counterexample doesn't occur if you have embedded mean convex mean curvature flow. So it's you kind of hope that you can try and prove this cylindrical and gradient estimate if you assume that our surface is embedded initially. So this theorem, so I think originally, I mean, I haven't read this paper, but it was proven by Brian White. And then, there's another paper by Sheng and Wang where they introduced this idea of non-collapsing, which we'll use. And they prove that the Grim Reaper can't occur. And then there's the proof that I'll talk about, which by Ben, which kind of uses this explicit formula for non-collapsing for the inscribed radius. So yeah, so I'll spend a little bit of time talking about non-collapsing here. The point is that, okay, so let's take some kind of, non-collapsing. So let me draw some kind of surface like this. Right, so let's say take this point X here. So I want to try and, so the property of the Grim Reaper, in order to kind of rule out that the Grim Reaper occurs as a blob limit, what we need is some kind of scale invariant quantity, right? So we're taking blow up, so the quantity we study has to be scale invariant. That rules out this kind of behavior at infinity where you have two flat parts that are separated by some kind of very finite interval. Okay, so the quantity that we can study is we'll look at the smallest ball that fits inside the surface. Okay, we'll call this the inscribed radius, and I'm not really talking about the inscribed radius, but I'll talk about the curvature, which is the inverse of that quantity. And to make it scale invariant, we'll look at mu divided by h. Okay, so if h goes to 0, but mu remains finite, then this quantity will go to infinity. So this quantity, it won't be bounded. So what we'll prove is that this quantity is actually bounded. So actually, we can write down an explicit formula for this. So I'll define mu of x, y, t as 2 x of xt minus x of y t times inner product with the normal vector at x divided by the length of this vector. That's great. Yeah, so what is this quantity doing is, so if I take a point x and any point on the surface and I draw, and I'll just draw a circle first, right? Then this mu of xy is this unique ball that's tangent to the surface at x and passes through the point y. Okay, so that's unique because we'll have three conditions. So it has to pass through X, has to be tangent to the surface at X, and has to pass through Y. So this is unique. And the sign is such that if the normal vector, if like this, if near X, this ball is kind of on the normal vector, the inward pointing normal vector to the ball is also the inward pointing normal vector to the surface at X, then this quantity here is positive. Okay, so this is positive, but if I had something like this, that's not really a ball, but yeah. So if it intersected on the other side, this would be this mu would be negative. But that's the very bad ball. But anyway, so now if I want to find the smallest ball that's contained inside this inside the surface, then I just have to take mu bar of x comma t and take a supremum over all y in m not equal to x. So this quantity is called the inscribed radius. So the goal here is to show that if that mu bar divided by h is bounded. Okay, so if it's bounded, then so you can see that mu scales. If I double mu scales the same way as h scales. So if I take a blow-up sequence going towards the Grim Reaper, then this would have to go to infinity. Okay, so one thing is that you can see that so firstly, this inscribed radius, because it's always contained inside the surface, you know that mu bar is always greater than zero, right? Because the surface is compact, right? And at the same time, you also know that mu bar is less than or equal to the it's always greater than or equal to the largest principal curvature at the point. Okay, because it's because you have a surface here and you have this ball on the inside of it. So the curvature of that at that point has to be greater than the largest principal curvature on the outside. And maybe also I can say that if these two things are equal, then what it means is that the point y where this supremum is attained is actually equal to x. So you take some limit. The supremum is not contained in this set. It's actually attained in a limit as y approaches x. Okay, so yeah, I'm not actually going to do this calculation. It's quite long, but it's not that difficult. It's how do you do it? So let me just so theorem is the evolution of mu. If I take the heat operator on mu.
Sorry, Vishnu. Yep. I just want to clarify. So the mu is 1 over the inscribed radius, right? It's not the inscribed radius.
Yeah, that's right. Oh, sorry. Yeah,
yeah.
No, what I said.
Okay. Yeah.
Inscribed curvature.
Yeah. Okay. Thanks.
Yeah, that's right. So the heat operator on mu is less than or equal to a squared mu bar minus 2 times this thing, this kind of first order terms. In the set, mu is greater than lambda n. In this set, this is true, but actually, I don't really, to do this cylindrical estimate and to do this kind of difficult stuff, you do need to look at this term here. But actually, if I get rid of this statement here in the set lambda mu greater than lambda n, and I also throw out this gradient term here, then I just get the quantity partial t minus Laplacian mu bar is less than or equal to a squared mu bar. Okay, that's true in the viscosity sense everywhere. So just like, I haven't really said, mu is not even differentiable, so it's not quite, I should probably say what that means. But anyway, let's just do this calculation of evolution of mu bar divided by h. So if I do mu bar divided by h, well, then what I'll get is less than or equal to partial t minus Laplacian of mu bar divided by h minus partial h, mu bar partial t minus Laplacian h divided by h squared plus gradient term. And that will actually give me, these will cancel out, right? Because, well, remember that the evolution of h is equal to h a squared. So one of the h's will cancel out here, and I'll have a mu there. And so then in the end, I'll just get 0 plus grad. So from that, I can immediately conclude that mu of this quantity is bounded by its initial value. So, at this point, I've already, we already know that the Grim Reaper can't occur as a blow-up limit just from this calculation here. Okay, you don't even have to do this, have this term here, or have this restriction. But it seems like to do this sharp estimate, you do need to take advantage of these terms here. So now, well, maybe I should say what I mean by this is true, because mu bar is only Lipschitz. What I can say, so what it means is that, so this inequality is satisfied in the viscosity sense, which means that if I take some point x bar, comma t bar in m times 0t, and if I have a function phi, which is defined from some open set that contains x bar and some backwards interval containing t bar to r, is smooth, a smooth function. And phi at this point is equal to mu at this point. But outside, just in a neighborhood, we have that it's on it phi minus mu bar is greater than or equal to 0, right? So phi and mu bar touch at the point xt, and in this neighborhood mu, u, and this backwards interval of t, phi and mu are on one side of each other. Then this phi has to satisfy this differential inequality. So partial t minus Laplacian of phi is less than or equal to a squared phi minus 2 equals 1 n di phi squared phi minus lambda I. Okay. So this is the inequality we have to prove for functions phi that satisfy this property. Okay. Oh, actually, so I also did something kind of that's not really, that's maybe a bit questionable. I've applied the maximum principle here to show that, to prove this, but the function mu is only defined on is not defined on a compact set, right? So maybe that's not quite right, but as it turns out, you can treat the kind of, if I take a limit as x approaches y, then this quantity here, you can see is actually is kind of like, it's the second fundamental form acting on a vector in the direction that you're taking this limit on, right? So if you want to make this argument fully correct, you can also, if you want to convince yourself, you should compute the evolution of the principal curvatures, like the smallest and largest principal curvatures, and show that that also satisfies the same inequality here, and then you can use the same argument. Okay, so so I'm not going to do this calculation, but what I'll do is I'll just kind of maybe suggest what you should do to solve this. Okay, so well, what we do is what we could do is we can just take this function mu, this expression here mu, and we can just calculate the Laplacian of this function and then compute the time derivative of the function. Those are all, that's all stuff you can calculate because it's x, all these quantities, you know how they evolve under mean curvature flow, and then you can, plug that in here and then, yeah, you try that out like that. But maybe it's slightly easier to consider a slightly different function, z, x, y, t, which is equal to half phi x of x comma t minus x of y comma t squared minus x xt minus x of y t comma normal vector at x. And now compute the time derivative of z and compute all these quantities, right, in normal coordinates. So, and then so doing this calculation is mostly straightforward. You also have to kind of make some clever choices of what coordinates, the way your coordinates about x and y are kind of set up. But then, the paper does this calculation completely explicitly. There's nothing left out really, and so yeah, and so in the end, what you get is that partial t z minus this Laplacian, which is this thing here, yep, so this quantity, what you get is kind of exactly what you want. You get partial t minus Laplacian of phi minus a squared phi minus 2 sum I equals 1 n of times this quantity. So, I mean, basically what we've done is we've taken the quantity mu, and then to make the calculation simpler, multiplied it by omega, right? And then, not omega, multiplied it by this quantity x, this difference between the distance squared between x and y, and then computed with that quantity. Okay. So yeah, so that's kind of how these kinds of calculations usually go. They're, the paper by Ben or by Brendler has this calculation pretty much in full detail, and it's not too difficult to follow. So now maybe I should state, so why am I mentioning this inscribed radius? The point of it is we're replacing we want to use it to kind of replace the statement of the cylindrical estimate. So, so one thing you should note is that this quantity mu bar is actually equal to h Oh well, okay. So is it actually equal to h? It's a const. It's like let me see. So
on a cylinder, is that what you're?
yeah, it's not equal to nh.
No, it'll be equal to h. Depends on your convention for h, I suppose. But if kappa 1 is 0.
Oh, so okay. So mu.
It will be.
Oh right. Yeah. Right. Yeah. Kappa 1 is 0.
N equals
right?
2
Okay.
only, right?
Yeah. Right.
Yeah.
Yeah, that's right. So yeah. Okay. So on a cylinder, mu equals h. So if you're just R cross S1 on the round cylinder, mu bar equals h. Okay. So the goal here is to kind of show that if you take a blow-up limit at a point where h goes to infinity in two-dimensional mean convex mean curvature flow, then you either get mu equals h. Yeah, if it's a cylinder, you get mu equals h. Okay, so let's write down a theorem. But the point is that this inscribed radius is kind of the thing you want to use to replace this kind of quantity here, for the cylinder, which is the difference between the two principal curvatures here. All right, so let's take a solution m cross 0t, which is mean convex mean curvature flow. Sorry, that's R3, isn't it? Then for all epsilon greater than 0, there exists a C epsilon greater than 0 such that whenever h is greater than or equal to C epsilon, we get mu bar is less than or equal to 1 plus epsilon h. So now if I take some kind of blow-up limit where h goes to infinity, using this theorem, I know that the inscribed radius of the limit is now 1. Oh, sorry, is equal to h. Oh, yeah, equal to h. So, okay, so I'm not going to do the full proof of this. I'm just going to maybe look at a certain part of it. So, so the proof here is the same as kind of the proof of the convexity estimate, cylindrical estimate, Huysken's theorem. We define some kind of function f, sigma comma epsilon, which is equal to h to the sigma minus 1, mu minus 1 plus epsilon h, minus c 0 comma epsilon. So I'm leaving out quite a lot here from the actual paper because there's another long calculation that needs to be done with related to the inscribed radius, and that uses the convexity estimates that we proved earlier quite a lot. So this constant here, C0 epsilon, is actually the same constant that you get when you do the convexity estimate. Okay, I don't fully understand really why that particular calculation in the paper is done, or what motivated doing that. But anyway, yeah, then let's define f sigma comma epsilon plus to be max 0 comma f sigma epsilon, and then quite a long calculation that I don't fully understand all of. I mean, I understand the calculation. I don't understand how some of the kind of that certain parts of it, why they were done. So f sigma epsilon plus the power of p d mu t is less than or equal to some constant c1, which depends on a bunch of parameters, f sigma epsilon plus the p d mu t plus c2 mt a squared d mu t. So yeah, so this is in a lot of these calculations, what we want to do is we want to show that this LP norm of f sigma epsilon plus is bounded. And that's maybe, in Huysken's theorem, how do you do that? You calculate this, you look at this quantity, you look at its time derivative, and you show that the time derivative of this quantity is less than or equal to 0, so it's bounded by its initial value. In this case, this doesn't look like it's less than or equal to 0, but that doesn't really matter because we can, remember that mean convex surfaces satisfy this inequality, right? So this a squared over here, I can replace that with less than or equal to C1 MT now here I get, I'll use C again, I guess. C to C H squared, okay? But H squared, the integral of H squared over MT, that's equal to the derivative of just the volume of M. So this derivative can be brought to this other side. So I get d on dt of f sigma epsilon plus minus constant c dash. This thing is less than or equal to C1. So C1 dash integral MT of F sigma epsilon plus P. And now I'm just adding on the same thing, C dash. So now, I mean, this is just the derivative of function is less than or equal to constant times the same function. So I know that this quantity is less than or equal to, so minus C dash, that's less than or equal to e to the kt times some constant c, well, okay, times this same integral times 0. But I know that, e to the kt, that's bounded by e to the k times the maximal time slice, so the maximum time, which is finite. So then I get c dash dash. The whole thing is bounded by some constant. So now, to finish off this, well, the rest of the argument, I mean, I think it's very similar to what Devesh did, the calculation Devesh did for the convexity estimates a while ago. So I'll just leave it there because I didn't want to do that whole argument all over again. Okay, so that's the cylindrical estimate. Does anyone have any questions about that? So I'm kind of more interested in this gradient estimate because I think the argument is quite nice compared to the previous one that I did, which was it was a kind of just a calculation and I didn't find it that interesting. But this argument is quite nice. So we want to use some kind of, actually the thing is that, I mean, I use this non-collapsing to prove the cylindrical estimate, and actually the gradient estimate is proved quite similarly. So I don't have enough time, I don't think, to prove the whole gradient estimate, but I'll write down the theorem. So let's take some kind of solution to mean curvature flow, mean convex embedded mean curvature flow. So kind of just want to give the idea of this theorem. Let's see. So now if I know that the mu hat divided by h. Okay, satisfying is less than equal alpha. And okay, so I actually didn't introduce the x-scribed curvature. So if I have a surface, I define this largest ball that's on the interior. At the same time, I can also define the largest ball that fits on the exterior. Okay, so that radius there, I've called the inscribed, the x-scribed curvature. I'll put a lower bar here. Okay, so if I have, and okay, so if this ball is on the outside of the surface, then this quantity here is negative. Okay, so the same calculation that's done for the inscribed radius also tells you that the x-scribed curvature is bounded below by minus, let's say this, use the same constant minus alpha. Okay. Oh, actually, I'll need 2 bars there, don't I? Okay. So if I have something that has this interior non-collapsing property and the exterior non-collapsing property, then in a parabolic neighborhood, I'm not really writing this theorem properly because I'm going to prove it next week. Of this point x, we have some kind of bound on the curvature. Okay, so I actually didn't write this part down, so I'm trying to figure out what these numbers are. It should be minus k there, c minus k. Yeah, so maybe I just want to say, like, why would non-collapsing have anything to do with kind of a gradient estimate? Well, the point is that if you have a point where the surface is non-collapsing, then that's telling you that you always have this interior ball and exterior ball around your surface where the surface is kind of pinched between these two things. So I know that mu, this quantity, that's greater than or equal to my highest principal curvature, and my inscribed curvature is less than or equal to my smallest curvature. So you kind of expect that these two should give you some kind of bound on the norm of A, right? Because it's giving you some kind of bound on the giving you some kind of bound on what the minimum maximum principal curvatures can be. And at the same time, that should also give you a bound on what the norm of the second fundamental form should be. Okay, so now if I know that that A is bounded, then that's all I need to prove, because then I can use these kinds of interior estimates by Huisken to prove that these higher derivatives are also bounded. CK. Okay, so next week, what I'll do is I'll prove that. I'll prove this theorem here for the case where K is equal to 0. Okay, so now I haven't fully decided how I'm going to prove this, because it seems to me that you don't actually need this second condition here, and you can just use the convexity estimate, but I haven't fully figured that out yet. But yeah, so next week I'll give this nice slick proof as to this estimate here. I think I'll stop there. Does anyone have any questions?
Awesome, thanks for that, Vishnu. Let's everyone thank our speaker. Does anyone have anything that they would like to discuss further or ask Vishnu about? anything casual or anything deeper if you'd like. Doesn't have to be a piercing question. All right, well, apparently, Vishnu, it was a exceptionally clear talk. Nothing's left to the imagination. So let's thank Vishnu again for a nice talk.
Thanks, Vishnu.
Yeah, very nice.
All right, thanks very much, Vishnu. I'll stop recording there.